Hi guys, welcome back to our lecture series on thermodynamics. So we'll continue where we left off from our last lecture, which focused on the derivation of entropy as a thermodynamic parameter from the Carnot cycle. Okay, we also looked at some calculations of entropy changes for very simple processes. Okay, so while we've been able to define entropy as a reversible heat flow in a process over the corresponding temperature, so in other words, ds is equal to dq rev over t, the concept of entropy can get a little abstract, so it's helpful if we get a molecular interpretation of entropy. Okay, so that is, what is it exactly, and how can we relate it to something a little bit more concrete? Okay, so let's consider the last process that we discussed previously, which is the isolated mixing of two ideal gases at constant temperature and pressure. Okay, so let's review. The mixing of two ideal gases occurs at isothermal and isobaric conditions. So intuitively, we know that if we remove the barrier between these two gases, okay, the gases will spontaneously mix to form a homogeneous mixture. But as we discussed before, this process is driven solely by an increase in entropy. Okay, so if we look at the different parameters for the system, there's actually no change in internal energy, enthalpy, especially since we're dealing with an ideal gas, and Q is equal to 0, and work is also equal to 0 since we're dealing with an isolated system. Okay, so it's only entropy that is non-zero for this process, and we found that entropy increases after mixing. Okay, so what else increases after mixing? So we could also see that probability is also maximized. Okay, so upon removal of the barrier, a homogeneous mixture is going to be our final equilibrium state because it is the most probable. Okay, so it's highly unlikely that upon removal of this barrier that the gases will stay unmixed in this particular state over here. Okay, so imagine that you have a gas and you remove the mixture, and then after a while you still have gas A and gas B on one side. Okay, so that is very highly unlikely. Okay, so this also tells us that if we start with this homogeneous mixture over here, it is also highly unlikely that the reverse process will occur. Okay, that we will go into a state in which it is now unmixed. So this explains irreversibility in spontaneous processes. Okay, so if we have a non-spontaneous process, it's not necessarily impossible, but it's definitely highly improbable. Okay, so overall, processes tend to proceed in directions that maximize probability, or you could look at it as disorder, up until a state with maximum probability and disorder, which is the equilibrium state. Okay, so how can we mathematically relate entropy and probability? Okay, so we want to get probability as a function of entropy. Okay, so let's consider how entropy is an extensive property and also some properties of combining probabilities. Okay, so let's look at the system over here, which is divided into two parts. Okay, so part 1 has entropy 1 and probability 1, whereas part 2 has entropy 2 and probability 2. So we know that total entropy will be the sum of the entropy of its parts. Okay, so we could write down S, the total entropy of the entire system, as S1 plus S2. So this is consistent with the fact that entropy is an extensive property. Okay, however, if we want to combine the different probabilities of part 1 and part 2, okay, usually this is done through multiplication. Okay, so the total probability of the system, okay, will be the probability of part 1 times the probability of part 2. Okay? Okay, so ultimately we could express this as, okay, so S, the total entropy, okay, so S of probability 1 times probability 2, okay, so this is going to be equal to S of probability 1 plus S of probability 2. Okay, so what function will give us this type of relationship? Okay, so hopefully this reminds you of logarithms, okay? Okay, so we could write this as S is equal to some constant. Okay, so let's use natural logarithm ln omega. Okay, so let's write this as k ln omega 1 plus k ln omega 2. Okay, so using the properties of logarithms, this could give us k ln omega 1 times omega 2. Okay, so based on our definition over here, this can be written as S of omega 1 times omega 2, okay, which is what we wanted to get. All right, okay, so basically this is Ludwig Boltzmann's definition of entropy. Okay, so this ultimately relates entropy with probability. Okay, so omega, this is also known as the number of microstates for the system. Okay, so this tells us the different number of ways to distribute the particles in the system. And K over here, this is Boltzmann's constant. Okay, so recall again, the Boltzmann's constant is 1.38 times 10 to the negative 23 joules per Kelvin. Okay, so note that the units is consistent with the units of entropy. Okay, so there's actually a whole field of physical chemistry that relates probabilities. Okay, so this is your statistical mechanics. Okay, so ultimately we could view entropy as a measure of probability. Okay, oftentimes, however, it's also related to disorder or chaos. Okay, a better way to look at it, however, is as a distribution of energy. Okay, so to summarize all this, for an isolated system, we know that energy is conserved. So this is the first law of thermodynamics. And it is the distribution of that energy, which is related to entropy, that determines the direction of spontaneity. Okay, so this second part is ultimately the statement of the second law of thermodynamics. Okay, so we could use entropy as a basis to tell us the direction in which processes occurs. All right, so let's look at some important implications of our molecular interpretation for entropy. Okay, so we know that entropy is related to the distribution of energy. Okay, so what happens if we start removing energy from our system? Okay, so we could do this by heat flow out of the system. Okay, so recall that heat flow is a type of energy transfer that changes the random molecular motion of the system. Okay, so if we have heat flow out, we tend to have a decrease in random molecular motion, and we also have a corresponding decrease in temperature. Okay, so upon decreasing the temperature, we're going to decrease the entropy, and since entropy is related to probability or the number of microstates, decreasing the entropy also decreases the number of microstates. Okay, so what happens if we continuously remove heat? Okay, so we're continuously removing heat. Okay, so we're continuously decreasing the temperature and we're decreasing the entropy. Okay, so what's the limit of the number of possible microstates? Okay, so the limit for the lowest possible number of microstates, recall that this is the number of ways to arrange it. Okay, so the lowest value for omega is equal to 1. Okay, so the implications of this is if we continuously remove heat, okay, and we continuously decrease the temperature of our system, okay, there will come a point where we will have the number of microstates as equal to 1, as in there's only one possible way to distribute our energy or arrange the particles in our system. Okay, so based on our definition of entropy, S is equal to K ln omega. So what happens when omega is equal to 1? Okay, this means that our entropy is equal to 0. Okay, so we could represent all of this mathematically using limits. Okay, and this is ultimately our third law of thermodynamics. Okay, so if we remove heat from our system, we remove energy from our system, and we decrease the temperature all the way to 0 Kelvin, which is the lowest possible temperature, our absolute entropy also approaches 0. Okay, so this is for a perfectly crystalline material. Okay, so the third law of thermodynamics establishes a theoretical limit to the possible temperature as well as the possible value of entropy. Practically speaking, however, it's impossible to reach absolute 0, so this is just a theoretical limit. Okay, but the importance of the third law of thermodynamics is that it establishes this over here. Okay, it establishes the conditions at which our entropy is defined as 0. Contrast this with our other state functions such as internal energy or enthalpy. Okay, recall again in our discussion of the first law of thermodynamics, when we were defining internal energy, we defined it as the total sum of kinetic energy and potential energy. Okay, so there's loads of different types of potential energy, right? So it's very, very difficult to quantify all of that. So we don't really have an established 0 value for internal energy. Okay, so that's why we never define the absolute values of internal energies or other state functions, but we can do that with entropy because we established a relationship between entropy and the number of microstates, and we were able to set a value for when the entropy is going to be equal to 0. Okay, so this is going to allow us to determine absolute values of entropies for our different systems. Okay, so namely, we could get absolute values of entropies for different compounds. Okay, so actually, if you flip back to the back of your physical chemistry textbooks or general chemistry textbooks, we see this right over here. We see standard molar entropies. Okay, so our standard molar entropy is set at standard pressure, 1 bar, and they're usually tabulated at 25 degrees Celsius, which is considered to be the standard temperature. Okay, so note, however, the difference between the tabulated values of enthalpy and Gibbs free energy, which we'll talk about a little later, and what's tabulated for our standard molar entropies. Okay, so enthalpies over here, they're tabulated as standard molar enthalpies of formation. Okay, so these correspond to the formation reaction of compounds. Okay, standard molar entropy, on the other hand, okay, this is not equal to entropy of formation. Okay, so let's just write that down. Okay, so standard molar entropy, this is not equal to delta S naught formation. Okay, so this is not equivalent. Okay, so this is a very common mistake. Okay, so please note the difference between these two. Okay, so note for the tabulated values, there's no delta sign. Okay, so actually the standard molar entropy corresponds to the entropy change of the compound from its 0 state at 0 Kelvin all the way to the corresponding temperature, which is usually 25 degrees. Okay, so technically, yes, it's a change, but it's a change from a 0 state. Therefore, we could treat this as an absolute value. Okay, so delta S naught formation, on the other hand, corresponds to the entropy change related to the formation reaction. Okay, so this has to be calculated from Hess's law using these standard molar entropy values, which we'll see later on. Okay, so note another thing too. Okay, so in our previous definition for formation reactions, we said that the standard molar enthalpies of formation for elements in their standard state is going to be equal to 0. However, note that for elements in their standard states, note that for its standard molar entropy, however, it is not 0. All right? Okay, so S naught, our standard molar entropy, is going to be 0 only at 0 Kelvin, right? Okay, so again, note the difference. All right, so how exactly is our standard molar entropy calculated? Okay, so let's start with our very basic definition of entropy. Okay, so ds is equal to dq reversible divided by temperature. Okay, so for our standard molar entropies, we're calculating the entropy at standard conditions, which is just at 1 bar. Okay, so ultimately we have constant pressure conditions, so we could rewrite this as dqp divided by t. Okay, so ds naught, this is just ncp dt divided by temperature. Okay, so if we're integrating this, okay, we could integrate this from the initial state, which we could set at 0 Kelvin, the entropy at 0 Kelvin, all the way to the entropy of the temperature of interest. Okay, so our limits over here for the temperature, okay, so 0 Kelvin all the way to the temperature of interest. All right, so upon integration, this is actually going to give us a delta S. Okay, so this delta S, when expanded, is going to be the entropy at temperature T minus the entropy at 0 Kelvin. Okay, so this is just going to be equal to 0 Kelvin to temperature ncp dt divided by T. All right. However, based on the third law of thermodynamics, we already defined what this is, right? Okay, so the entropy at 0 Kelvin, this can be just set as 0. Okay, so ultimately when we're calculating the delta S from our initial state at 0 Kelvin to the temperature of interest, this is just equivalent to the entropy at the temperature of interest. All right, so that is why when we're looking at tabulated values for standard molar entropies, we no longer see this delta sign anymore because we established a value, an absolute value for our initial state, which is just equal to 0. Okay, so the values that we calculate here is pretty much now just an absolute value of entropy. All right, so it's actually not as simple as it looks over here, actually. You need to take into account the different types of heat capacities and the different phase changes that you undergo when you're going from 0 Kelvin all the way to temperature T. Okay, so let's look at a plot of the different heat capacities with temperature. Okay, so we'll start from 0 Kelvin. Okay, so actually for many substances, it's very, very difficult to determine the CP at very low temperatures. Okay, so typically what we use instead is the so-called Debye-Third power law, which tells us for solids at very low temperatures, the heat capacity is proportional to the temperature raised to 3. Okay, so this is, for the most part, an approximation. Okay, so this is our first entropy change that we need to take into account all the way to a certain temperature TD. Okay, so after this, we could start looking at data that tells us the heat capacities of the solid. Okay, so this part here takes into account the entropy change upon increasing the temperature of a solid. Okay, so once we hit the melting temperature, however, we need to take into account the entropy change associated with fusion. Okay, so we're transforming our solid to a liquid. So if we have a phase change going from a solid to a liquid, we definitely know that we have a corresponding increase in entropy. Okay, so the temperature is going to remain constant, okay, but our entropy has to be taken into account here. Okay, so let's just have a dotted line here. And once we convert our solid completely into a liquid, okay, we could start heating up that liquid, okay, using the CP of the liquid up until the boiling point. Okay, so at the boiling point, again, you need to take into account the entropy change associated with the boiling process or the vaporization process. Okay, so this occurs at constant temperature, and once we convert all our liquid to a gas, okay, we could now take into account the CP of the gas in order to calculate the entropy change associated with that. Okay, so we need to go through all of these different steps, especially if your final temperature is at this point over here. Okay, so let's look at how we could sum up all of these entropies in order to calculate our standard molar entropy. Okay, so when we're calculating our standard molar entropy, okay, so this is going to be delta S naught. Okay, so this is going to be the entropy at the desired temperature minus the entropy at 0 Kelvin. Okay, so this is going to be the sum of the different parts that we just discussed. Okay, so delta S1, okay, so that's 0 Kelvin to a certain temperature, okay, plus delta S2 plus delta S3 plus delta S4, delta S5, and delta S6. Okay, so this part over here, this corresponds to our approximation. So we'll be using the so-called Debye-Third power law. Okay, so this part over here, this corresponds to when we could consider the CP of the solid. Okay, so this is all the way up until the melting temperature of our compound, and delta S03, this corresponds to the fusion process. So this is going to be at constant temperature, the melting temperature. Okay, delta S04, this corresponds to the CP of the liquid phase all the way up until the boiling temperature. Okay, so delta S05, this corresponds to vaporization, and delta S06, finally, this corresponds to using the CP of the gas, okay, up until the temperature of interest. All right, so the calculation of this, okay, so delta S01, the Debye-Third power law, this tells us that CP is equal to A times T raised to 3. Okay, so this will just be A raised to T3 divided by T dt from 0 to TD. Okay, so this is delta S01. Okay, so our delta S02, okay, we need to make sure that our temperatures are going to be continuous. Okay, so we start from TD all the way to the melting temperature. Okay, so we need to take into account the CP of our solid. Okay, so this is going to be the CP of the solid divided by T dt. Okay, so next we have the fusion process. Okay, so this is just going to be equal to, so we have a constant temperature process. So you could write this as delta H fusion divided by the temperature, okay, which is Tm, right? So the next part is when we increase the temperature of our liquid now, okay, so we start from Tm all the way to the boiling temperature. So this is going to be equal to Cp of the liquid divided by T times dt. Okay, so this is delta S naught 4. Okay, so delta S naught 5 takes into account vaporization, so this is a constant temperature process. So this is just the enthalpy of vaporization divided by the boiling temperature. Plus, finally, okay, we need to take into account now increasing the temperature of our gas. So we start from Tb all the way to the temperature of interest. Okay, so this is going to be the Cp of the gas divided by T times dt. Okay, so this is the method to calculate the standard molar entropy. Okay, so all of these different steps have to be taken into account. All right. Okay, so understanding the different process in order to calculate the standard molar entropy can also help us understand the differences between the tabulated standard molar entropy values that we see. Okay, so for one, okay, we definitely could note from this table over here that the standard molar entropy of different phases will be different. Okay, so for example, the standard molar entropy of liquid water is 69.9, whereas that for the gaseous state is a much higher value, 188.8. Okay, so qualitatively speaking, we know that there's greater disorder in the gaseous state rather than the liquid state. Therefore, we see a higher standard molar entropy value for the gaseous state. Okay, so we could also see some additional trends in terms of molecular weights. Okay, so if we compare these gases over here, okay, we could note that if we have a higher molecular weight, okay, so starting from H2 all the way to O2, we tend to have a higher standard molar entropy value. Okay, so this can be understood qualitatively. Okay, so if we have a higher molecular weight, we tend to have a greater number of electrons or a greater number of different types of atoms. Okay, so this allows greater motion and greater ways of distributing the energy in that compound. Okay, so we could also use these tabulated values of standard molar entropy in order to calculate the entropy changes associated with reactions. Okay, so this is just going to be an application of Hess's law. Okay, so in order to calculate the standard molar entropy change for a reaction, we just sum the standard molar entropies of the products and just subtract the standard molar entropy values of the reactants. Okay, so this is just a standard application of Hess's law. Okay, so we could also calculate the variation of temperature of our standard molar entropies of reactions. Okay, so note previously when we were doing this for enthalpy, we used something called the Kirchoff's rule. Okay, so entropy also has an equivalent version of Kirchoff's rule. So we're interested in determining the variation of temperature of this entire expression. Okay, so we could just get the derivative of this entire expression with respect to temperature at constant pressure, of course. Okay, so rewriting this, we get the partial derivative of delta S reaction with respect to temperature at constant pressure. Okay, so this is going to be equal to the sum of N times the partial derivative of S naught products with respect to temperature at constant pressure minus the sum of N times the partial derivative of S naught reactants with respect to temperature, all at constant pressure. Okay, so these are your standard molar entropies of your compounds. Okay, so we could define that as ds naught is equal to Cp dt over T, assuming that we won't have any phase changes. Okay. All right, so we could rearrange this expression in order to get a derivative. Okay, so recall that this was in constant pressure conditions. So if we transfer the differential of dt on the other side, we get partial of S naught with respect to T at constant pressure is equal to Cp naught over T. Okay, so we can make the corresponding replacement over here. So this is going to be the sum of N times Cp naught over T of the products minus N times Cp naught of the reactants divided by temperature. Okay, so this essentially, this term on top over here, this is essentially delta Cp. Okay, so partial of delta S naught reaction with respect to T at constant pressure, this is just going to be equal to delta Cp naught divided by T. Okay, so rearranging this, okay, we could get d delta S naught reaction, okay, is equal to delta Cp naught divided by T times dt. Okay, so we could integrate this expression in order to get entropy changes of our reaction at different temperatures. Okay, so keep in mind again that we need to use a reference state, and this is going to be assuming that we won't be having any phase changes involved for the different products and reactants. Okay, so let's try out this equation with the next problem over here. Okay, so in this problem, we want to calculate the molar entropy of formation of ammonia at 1000 Kelvin given the following. Okay, so we're given the standard molar entropies of ammonia, nitrogen gas, and hydrogen gas, and we're also given the corresponding Cp values. So before we begin, we need to write down the balanced chemical equation for the formation of ammonia. Okay, so the formation reaction corresponds to 1 mole of ammonia formed from its elements in their standard states. Okay, so this is nitrogen gas and hydrogen gas. Okay, so to balance out this equation, we need 1/2 of a mole of nitrogen gas, and we need 3/2 of a mole, 3/2 mole of hydrogen gas. Okay, so recall again Kirchoff's rule. Okay, so Kirchoff's rule for entropy, this is d delta S naught, in this case formation, is equal to delta Cp naught divided by T dt. Okay, so we're going to be integrating this, okay, from our reference state to our final desired state. Okay, so in this case, what's given here is the standard molar entropies at 25 degrees Celsius or 298 Kelvin. Okay, so 298 Kelvin is going to be our reference temperature state. And of course, our final state is going to be 1000 Kelvin. Okay, so we could calculate the enthalpy of formation at 298 Kelvin. Okay, so this is our reference state, and we'll be getting it all the way up until our desired temperature. Okay, so we'll be calculating the enthalpy of formation at 1000 Kelvin. All right. Okay, so let's just integrate this, but before we do that, let's calculate our reference state over here. Okay, so using Hess's law, okay, so let's calculate this on a fresh slide. Okay, so we could calculate delta S naught formation. So this is just Hess's law, products minus reactants. Okay, so we have 1 mole of ammonia per mole of reaction, so that is 192.5 joules per mole Kelvin, minus the reactants. Okay, so this is going to be 1/2 mole of nitrogen per mole reaction times 191.50 joules per mole Kelvin, plus 3/2 of a mole of hydrogen gas per mole reaction times 130.58 joules per mole Kelvin. All right, so punching this in your calculator will give you a value of negative 99.12 joules per mole reaction Kelvin. Okay, so we'll be using this value as our reference state once we use Kirchoff's rule. Okay, so recall again that Kirchoff's rule requires the use of our delta Cp. Okay, so we need to calculate our delta Cp. Okay, so my suggestion here is that since we're dealing with multiple terms, is that we calculate delta Cp term by term over here. Okay, so we just need to multiply each of the terms by the corresponding coefficients from the balanced equation. So for nitrogen, we had a coefficient of 1/2, and for hydrogen, we had a coefficient of 3/2. Okay, so Cp is also products minus reactants. Okay, so we'll be calculating this as 25.89 minus 1/2 times 26.98 minus 3/2 of 29.07. Okay, so upon calculating this, we get negative 31.21, and the same thing can be done for the second term over here. So this is going to be positive 30.88 times 10 to the negative 3 times t. Okay, so for simplicity's sake, I'll be expressing our delta Cp naught as A plus BT. Okay, so again, our expression for Kirchoff's rule was written as follows from our earlier slide. So this is delta S naught formation at 1000 Kelvin. Okay, so let's just transfer our reference state to the other side. So this is going to be equal to delta S naught formation at 298 Kelvin plus our integral over here. So this is 298 Kelvin, 1000 Kelvin times Cp naught over T dt. Okay? Okay, so let's evaluate this over here. If we replace our delta Cp is A over T plus B after dividing each term by T times dt. Okay, so this is at 298K to 1000 Kelvin. Okay, so upon evaluating this is going to be equal to A ln T plus B times T evaluated from 298 Kelvin to 1000 Kelvin. Okay, so this is just a major difference between using Kirchoff's rule with the entropy version versus the enthalpy version. Okay, so when we're calculating it for entropy, we need to make sure that we divide each of the terms in our delta Cp by temperature. Okay, so overall, upon evaluating delta S naught formation, okay, so we should evaluate this integral and add our value for delta S naught formation at 298 Kelvin, we should get negative 115.2 joules per mole reaction Kelvin. All right. Okay, so just be careful about calculating your term over here. Okay, make sure you divide each of your terms in your delta Cp expression by temperature. All right. Okay, so overall, we now know how to calculate the entropy changes for all different types of physical processes, which we discussed in our last lecture, and we also know how to calculate the entropy changes for chemical reactions. Okay, so note, however, that when we've been calculating this, we've been calculating only the entropy change for the system. Okay, so we can't exactly use this value as a universal basis for establishing criteria. We could only use it if our system is an isolated system. Okay, so our criteria for spontaneity for an isolated system, recall, is that we could use the entropy change for the system alone as a basis. Okay, so if it's greater than 0, we know that it's an irreversible spontaneous process. If it's equal to 0, we know that we have equilibrium. And if it's less than 0, we know that we have a non-spontaneous process. Okay. However, most of the systems that we'll be dealing with involve non-isolated systems, okay? So if we're dealing with a non-isolated system now, our criteria for spontaneity is going to be the change in entropy of the entire universe. Okay, so in order to calculate this, we need to calculate the entropy change of the system and the entropy change of the surroundings, which is not very convenient, okay? So again, we defined the system as the part of the universe that we're interested in studying and the surroundings as everything else. So it's not very convenient to have to calculate the entropy change of the surroundings as well if we're just interested in determining the spontaneity of the process involved for our system. Okay, so ultimately our goal now is to establish an alternative criteria for spontaneity. Okay, so we want to express the second law in terms of other system state functions, okay, so that we could find an alternative criteria for spontaneity at convenient conditions. Okay, so what are convenient conditions? Okay, so think about the conditions right now and the conditions that you could establish easily in the lab. Okay, so that includes controlling different temperatures, so usually constant temperature, okay, and constant pressure. Okay, so we could also deal with constant volume conditions using specialized apparatus, but these are the ideal conditions that we want to have. Okay, constant temperature and constant pressure. Okay, let's look back at entropy as a basis for spontaneity criteria. Okay, so recall again that if we just use the entropy of the system as criteria, it only applies to isolated systems. Okay, so overall, we know that ds for an isolated system Okay, the criteria for spontaneity is that it has to be greater than or equal to 0. Okay, so let's consider what kind of parameters here are going to be constant. Okay, so let's consider what exactly is an isolated system. What's being held constant for an isolated system? Okay, so we know that for isolated system, there is no exchange of energy with the surroundings. So this means that the dq net of our process is equal to 0, and the dqw of our process is equal to 0 as well. Okay, so based on the first law of thermodynamics, du is equal to dq plus dw. So since all of these terms are equal to 0, so that means the change in internal energy is equal to 0. Okay, so for an isolated system, internal energy is constant. Okay, so du is equal to 0. This means there's no change in internal energy. So that means internal energy is constant. Okay, so if we have a system that is just involved in PV work, okay, we said that dw is equal to 0, and we also defined this as negative P external times dV. Okay, so since dw is equal to 0, this implies that dV is equal to 0 as well. Okay, so these are the parameters that remain constant in an isolated system. Okay, so we have constant internal energy, we also have constant volume. Okay, so overall, in general, at constant U, internal energy, and constant volume, okay, we could establish a criteria for spontaneity. So in general, the change in entropy when we have constant internal energy and constant volume is going to be the basis for our criteria for spontaneity, okay? So for spontaneous processes, ds at constant internal energy and volume is going to be greater than or equal to 0, okay? So this again is our criteria for spontaneity if we use the entropy change for our system as a basis for our criteria. Okay, so again, we mentioned how this isn't very convenient since it's very hard to establish constant internal energy and constant volume. Okay, so let's look at a more generalized statement for our second law of thermodynamics, which is our Clausius inequality. Okay, so we'll be using the Clausius inequality as a basis to look for different types of state functions that we could use as a basis to determine whether our process is going to be spontaneous or not. Okay, so overall, our Clausius inequality is dq over t. Okay, so dq, this could be for any type of process, doesn't have to be reversible. Okay, so this has to be less than or equal to ds for permissible processes. Okay, so let's rearrange this expression. Okay, we could write this as dq over t minus ds is less than or equal to 0. So let's multiply this whole term, this whole expression by t. So we have dq minus t ds is less than or equal to 0. Okay, so let's recall the first law of thermodynamics statement that we had. So that was du is equal to dq plus dw. Okay. Okay, so if we have a system that is just involved in pressure volume work, we could write this as du is equal to dq minus p dv. Okay, so we could express dq as du plus p dv. Okay, so let's replace this term for dq. Okay, we'll write du plus p dv minus t ds is less than or equal to 0 for spontaneous processes. Okay, so this is an alternative form of the Clausius inequality. Okay, so this is the general criteria for spontaneity. Okay, so the entire expression over here has to be less than or equal to 0 for spontaneous processes. Okay, so let's try to establish some constant conditions over here. Let's say that we set constant volume and constant entropy. Okay, so if we have constant volume and constant entropy, dV is going to be equal to 0, ds is going to be equal to 0. So that means this term zeroes out, this term zeroes out, and we're left with du. Okay, so du at constant volume and constant entropy, this is going to be less than or equal to 0 for a spontaneous process. All right? Okay, so overall, what this expression means over here is that for any system at constant volume and constant entropy, a spontaneous process is in which the change in internal energy is going to be less than or equal to 0. Okay, so this could be an alternative criteria for spontaneity, but note again that the conditions are not very convenient. Okay, so we have constant volume, which can be established, but it's not very easy to establish constant entropy. But we do know that for a spontaneous process, we could see that the internal energy has to be decreasing. Okay, so contrast this with entropy. Okay, so for entropy, a spontaneous process is in which the entropy is increasing for certain conditions. Okay, so note that there is a different relationship between the change in internal energy and the change in entropy for spontaneous processes. Okay, but keep in mind that we're pretty much looking at the same thing, but in different perspectives. Okay, so now let's try to see if we could use enthalpy as a basis for a criteria for spontaneity. Okay, so let's get a generalized expression for enthalpy. Okay, so a more general expression for enthalpy is as follows. Okay, so this will be H is equal to U plus PV. Okay, so it looks super similar to what we've been dealing with before. Okay, so let's try to get the differential of this expression over here. So this is just going to be equal to dH is equal to du. Okay, so we have a product of pressure and volume over here, so we need to use the product rule. So this is going to be equal to plus PV plus VdP. Okay, so let's recall the generalized expression for the Clausius inequality. Okay, so that was du plus PdV minus TdS is less than or equal to 0 for a spontaneous process. So we can see here that we could actually replace this expression over here with an equivalent expression from this expression over here. Okay, so we can see here that du plus PdV is equal to dH minus VdP. Okay, so we could rewrite the general expression for the Clausius inequality as dH minus VdP minus TdS is less than or equal to 0. Okay, so this is an alternative statement for the Clausius inequality in terms of enthalpy and in terms of changes in pressure. Okay, so we could establish some constant terms over here. Okay, so note that we have dP over here. So what happens when we have dP is equal to 0? We just establish constant pressure. And if we have ds is equal to 0, we just establish constant entropy. Okay, so when these things are constant, this term and this term is going to zero out. So that means dH at constant pressure and constant entropy is going to be less than or equal to 0 for a spontaneous process. Okay, so this is an alternative criteria for spontaneity at a given set of constant conditions, namely pressure and entropy. Okay, so while we have a relatively more convenient term here that's constant, we still have this problem over here with dealing with constant entropy. It's not very easy to establish constant entropy for the processes of interest. Okay, so we need to find alternative expressions in order to establish more convenient criteria for spontaneity. Okay, so overall, we can't rely on the current state functions that we know. Okay, so we can't rely on entropy, internal energy, or enthalpy as a basis for convenient criteria for spontaneity. Okay, so this means that we need to define new terms to use. Okay, so when we're looking for a criteria to use for constant temperature and volume, okay, so let's define a new state function, which we'll define as A. Okay, so A, okay, let's define this as equal to U minus TS. Okay, so if we get the total differential of this, similar to what we did with enthalpy, we'll get dA is equal to du minus TdS minus SdT. Okay, so let's recall our alternative form for the Clausius inequality again. So this is equal to du plus PdV minus TdS has to be less than or equal to 0 for spontaneous processes. Okay, so we can see here that we have several terms that are similar to our differential of A. Okay, so we could rewrite this as dA plus SdT is equal to du minus TdS. Okay, so we could replace these two terms over here with dA plus SdT. Okay, so let's rewrite this as dA plus SdT plus PdV is less than or equal to 0. Okay, so if we establish constant temperature and constant volume, okay, so that's going to be dt is equal to 0, dv is equal to 0, this term and this term is going to become 0. So that means that dA, okay, the change in our new thermodynamic parameter at constant temperature and volume, okay, this should be less than or equal to 0 for spontaneous processes. Okay, so note here that we have much more convenient conditions that are held constant. Okay, so constant temperature is easy to establish. Constant volume conditions can be established in specialized apparatus such as our bomb calorimeters. Okay, so this parameter over here, this A here, this is called your Helmholtz energy. Okay, so we'll get to the physical significance of this a little later on. But just keep in mind that by defining A as U minus TS, we were able to establish A as a criteria for spontaneity at constant temperature and volume. Okay, so overall, we could see that for spontaneous processes, this term over here, the change in Helmholtz energy, has to decrease. Okay, so now let's look at even more convenient conditions, which is at constant temperature and pressure. Okay, so let's define a new state function g. Okay, so g is equal to h minus ts. Okay, so again, let's get the differential of this expression. So dg is equal to dh minus tds minus sdt. All right. Okay, so let's also write down an alternative form of the Clausius inequality that we derived from our investigations of enthalpy. Okay, so when we're investigating enthalpy, we got the expression of dH minus VdP minus TdS is less than or equal to 0 for spontaneous processes. Okay, so we could rewrite this expression as dG plus SDT is equal to dH minus TdS. Okay, so we can see here that we could replace this term and this term with this term over here. Okay, so let's rewrite this. We get dG plus SDT minus VdP is less than or equal to 0 for spontaneous processes. Okay, so if we establish constant temperature and constant pressure, so that means dt is equal to 0 and dp is equal to 0, these terms again, they become 0, and our criteria for spontaneity at constant temperature and pressure conditions is going to be dg has to be less than or equal to 0. Okay, so again, for spontaneous processes at constant temperature and pressure conditions, this thermodynamic parameter has to be decreasing, okay, or it is minimized. Okay, so this thermodynamic parameter is called, as you are probably familiar with, your Gibbs Free Energy. Okay, so this is where your Gibbs Free Energy actually comes from. Okay, so it's an alternative statement of the Clausius inequality, okay, which was derived from the second law of thermodynamics, okay, and modified for more convenient conditions of constant temperature and pressure. Okay, so many of our further investigations of spontaneous processes and equilibrium will be using Gibbs Free Energy. Okay, so just to summarize all the different criteria for spontaneity and equilibrium, okay, so this is for entropy. So we know that for spontaneous processes, the entropy of the universe is increasing. Okay, so the equilibrium state corresponds to when the entropy change is 0, and non-spontaneous processes correspond to a negative entropy change in the universe. So ultimately, spontaneous processes, they're going towards states that maximize the entropy of the universe. Okay, so the equilibrium state corresponds to the maximum state. For our alternative criteria, on the other hand, okay, so we can look at when we have constant temperature and volume and constant temperature and pressure. So this corresponds to our Helmholtz and our Gibbs Free Energy. For both of these cases, we have the opposite. So this time, for spontaneous processes, the change in Helmholtz energy or the change in Gibbs Free Energy has to be negative. Overall, spontaneous processes tends to go towards a minimum Gibbs free energy or Helmholtz free energy. Okay, so when we're using these terms, our equilibrium state corresponds to a minimum Helmholtz or Gibbs free energy, and our spontaneous processes tends to go towards a minimum. Okay, so we tend to be decreasing in Gibbs free energy or Helmholtz energy. Okay, so next let's try to get a more concrete idea of what Helmholtz energy is and what Gibbs free energy is. Okay, so let's look at the physical significance of G and A. So let's start with the first law of thermodynamics. Okay, so let's write du is equal to dq plus dw. Okay, so we could rewrite dq as du minus dw. Okay, so we'll be using this expression of dq when we rewrite the Clausius inequality. Okay, so the Clausius inequality is ds is greater than dq over t. Okay, so let's just rewrite this as t ds is greater than or equal to dq. Okay, so let's replace the first law expression in this expression over here. So t ds is greater than or equal to du minus dw. Okay, so rearranging this, okay, we have dw has to be greater than or equal to du minus tds. Okay, so recall again from our derivations when we were discussing Helmholtz free energy, however, that this term over here, this is going to be equivalent to dA plus sdt. Okay, so let's just rewrite this over here. So dw, this is greater than or equal to dA plus sdt. Okay, so if we establish isothermal conditions where dt is equal to 0, this means that dw has to be greater than or equal to dA. Okay, so what does this mean exactly? Okay, so let's just integrate all of this. Okay, so that means that delta A, the change in Helmholtz free energy, is less than or equal to the work. Okay, so the significance of this expression over here tells us the physical meaning of delta A. Okay, so recall again that if our system is doing work, this term over here, this is going to be a negative value. Okay, so again, if this term is negative, this means that this work here is the work done by system. Okay, so this expression tells us that delta A is the lowest possible value of W, okay, the work done by the system. Okay, but since the work done by the system is a negative value, this expression means that delta A, okay, this is the maximum work that the system can do on the surroundings. Okay, so again, the Helmholtz energy, this represents the maximum work that the system can do on the surroundings. Okay, in other words, it's kind of confusing, yes, with all the negative signs and whatnot, but just think of it as that this term over here is the most negative value for work that we could have. Okay, so now let's look at the significance of Gibbs free energy. Okay, so when we're discussing the physical significance of Gibbs free energy, we'll start with a slightly extended form of the first law of thermodynamics. Okay, so we'll write the first law of thermodynamics as follows. Okay, so du is equal to dq plus dw. Okay, so dw can be split in many different forms. Okay, so there's many different forms of work that we can do, right? Okay, so we could have our PV work, which we've been discussing primarily, or we could also have alternative non-PV work. Okay, so what exactly is our non-PV work? Okay, so PV work, this could be electrical work, chemical work, etc., etc. Okay, so these are your different types of non-pressure volume work. Okay, so our expression, our extended expression for the first law of thermodynamics is du is equal to dq plus dw PV work plus non-PV work. Okay, so again, similar to our first treatment, let's write out an expression for dq, which we'll later input in our Clausius inequality. So dq, this is equal to du. Okay, so let's rewrite our pressure volume work as negative PdV. Okay, so upon rearrangement, that becomes plus PdV, and then we have minus our non-PV work. Okay, so again, let's input this in our Clausius inequality. So our Clausius inequality can be written as TdS is greater than or equal to dq. Okay, so that means that TdS is greater than or equal to du plus PdV minus dW non-PV. So let's rewrite this entire expression. Okay, so let's write this as dW non-PV work is greater than or equal to du plus PdV minus TdS. Okay, so note that this expression over here at constant pressure conditions can be rewritten as dH. Okay, so at constant pressure conditions, this is going to be dH minus TdS. Note from our previous discussion that dH minus TdS can be rewritten in terms of dG. Okay, so this expression, this is equivalent to dG minus SDT. Okay, so dG minus SDT, okay, this is going to be less than or equal to the dW non-PV work. Okay, so if we establish constant temperature conditions, okay, so this term becomes 0, so this means that dW non-PV work is less than or equal to dG. Okay, so upon integrating all of this, this tells us that delta G, okay, this has to be less than or equal to the non-PV work done by the system. Okay, so similar to our earlier statement with the Helmholtz, okay, so this time Gibbs Free Energy, this represents the maximum non-pressure volume work that a system can do. Okay, so that's why we call this free energy. Okay, so this is our delta G represents the energy that is free to do non-pressure volume work, such as electrical or chemical work. Okay, so pressure volume work, this is usually involved with expanding or compressing a gas against the atmospheric pressure. Okay, so some of that energy is already lost as unavoidable pressure volume work. Okay, so that's why we're interested in delta G, because again, this gives us the free energy in our system that can do other types of non-pressure volume work, okay, like electrical and chemical work. Okay, so let's just summarize the different parameters here. Let's compare and contrast our Helmholtz energy and Gibbs Free Energy. Okay, so Helmholtz energy, this represents the maximum overall work that a system can do, whereas for Gibbs Free Energy, this represents the maximum non-pressure volume work. Okay, so arguably the Gibbs Free Energy can give us more useful work over here, since we're not considering any pressure volume work that the system has to do against the atmosphere. Okay, so for definitions, A is equivalent to U minus TS, whereas G is equal to H minus TS, and the total differential is given as follows. Okay, so again, at isothermal conditions, we could rewrite the differentials as dA is equal to du minus TdS, or for Gibbs Free Energy, we could write this as dG minus dH minus TdS, okay, which is probably familiar to you guys, all right? Okay, so overall, this whole TdS term over here, this actually represents the energy or the enthalpy that is tied up in random molecular energy states. Okay, so recall again that in our previous derivations, we've been referring to TdS as just dq, right? Okay, so we could look at this term as the amount of energy that is unable to perform work. Okay, so this is the energy that we have to subtract when we're trying to figure out what the maximum work that we can do given our energy content of our system. Okay, so for the most part, however, we're mostly interested in Gibbs Free Energy since it gives us the most convenient criteria for spontaneity. Okay, so now let's look more closely on how we could calculate Gibbs Free Energy. Okay, so let's start with the basic definition of Gibbs Free Energy. So this is G is equal to H minus TS. Okay, so if we get a differential of this, this gives us dG is equal to dH minus TdS minus SDT. Okay, usually, however, we're more interested in isothermal processes, okay? So we usually establish dt as equal to 0. Okay, so this term zeroes out, and we get dg is equal to dH minus TdS, which when we integrate from the final and the initial states, okay, we get delta G is equal to delta H minus T delta S. Okay, so this is that famous equation that we all know that defines Gibbs free energy from the enthalpy change of the process and from the entropy change of the process. Okay, so for the most part, for isothermal processes, we could calculate delta G just by evaluating the enthalpy in the process as well as the entropy change. Okay, so we also have values tabulated for Gibbs free energy, which we saw earlier. Okay, so we also have a corresponding Gibbs free energy change for our standard formation reactions. Okay, so we could use those values in order to calculate the corresponding Gibbs free energy change for a reaction just by applying Hess's law. Okay, so this is just your standard products minus reactants equation. Okay, so we saw many of these types of equations before. Okay, so again, same with our definition for enthalpy. The Gibbs free energy change for elements in their standard states are expected to be 0. Okay, so we'll be looking at lots of different types of calculations for Gibbs free energy later on. Okay, so actually this serves as an introduction for the parameter of Gibbs free energy. Okay, so I'll be looking at Gibbs free energy in phase equilibria, which will be our next topic. And we'll also look at it more closely once we start looking at chemical equilibrium and electrochemistry. Okay, so let's just summarize what we discussed for our thermodynamics lecture series. Okay, so our first discussion was all about the first law of thermodynamics. Okay, so in this discussion, we learned how energy is conserved. We looked at different ways in which energy can be transferred from the system to the surroundings or vice versa. Okay, so we also looked at different types of ideal gas processes as well as chemical changes and phase changes. Okay, so what was missing from the first law, however, is that it didn't tell us anything about spontaneous processes. Okay, so this was addressed by the second law of thermodynamics, which introduced us to the term entropy. Okay, the third law of thermodynamics, on the other hand, helped us establish a zero value for entropy, which allows us to calculate our standard molar entropy value. Okay, so later on, we also used principles from the second law of thermodynamics in order to establish alternative criteria for spontaneity. Okay, so from here, we established and defined Gibbs free energy. Okay, so again, Gibbs free energy will be the primary star of our discussions later on. Okay, so we'll be looking at all different types of equilibrium systems. Okay, so we'll be looking at phase equilibria and chemical equilibria later on. All right, thanks guys.